Now I request Dr. C.H. Mohan Rao Garu, Chairman, NASI Hyderabad Chapter and ASTC, Professor D.N. Reddy Garu, former Vice Chancellor, JNTU Hyderabad and former Chairman RAC DRDO, and Madam Suma Varughese, Outstanding Scientist and Director General MEDC and SOS DRDO, to come on to the dais, please.
Welcome to the technical session. Now may I request Dr. Reddy, Professor D.N. Reddy, who is a former Vice Chancellor of JNTU and also Chairman of RAC DRDO, to kindly conduct these proceedings. Dr. Reddy, please.
Very good morning to all of you. Professor Dr. Mohan Rao Garu, former Director of CCMB, presently distinguished scientist. Suma Varughese, my erstwhile colleague at DRDO. Presently, she is the Director General of Microelectronic Devices and Computer Systems, DRDO and DZ. And other distinguished scientists, my former colleagues from Osmania University, JNTU. Good morning, and ladies and gentlemen. At the very outset, I would like to congratulate National Academy of Sciences, Hyderabad Chapter, Dr. Mohan Rao, ASTC, Mr. Narasimha Rao, jointly organizing this first Women Scientist Conclave in very apt at this point of time in IIC auditorium. In fact, morning, Tamil Sai Govindarajan, in fact, she is very humorous and delivering her speech. Everybody enjoyed her contribution to the women scientists. Particularly this Dr. K.V. Raghavan memorial lecture being organized now after the tea break. Dr. K.V. Raghavan is a well-known scientist. Particularly, he was the Chairman RAC DRDO, Minister of Defense during 2006 to 2009. And in fact, I succeeded him as a Chairman RAC in DRDO. Dr. Raghavan, he was also Director for 3 labs. He was RRL Jorhat. He was also Director for CLRI Madras, and he was also Director for IICT many years. So in fact, his contributions are immense for academic field and also visionary, and basically he was a human being. He was born in actually 1st October of 1943, but he also left us in October 2017 at the age of 74. In fact, he is a good friend of many of us. So he was a very close friend of me. In fact, we used to reside in the same colony. Very unfortunately with him, but on befitting to his occasion, Dr. Mohan Rao Garu, National Academy of Sciences and ASTC thought about organizing this particular memorial lecture, and his contributions are immense. If I recall briefly, particularly he was a Fellow of National Academy of Engineering, Indian Institute of Chemical Engineering, AP Academy of Sciences, and Distinguished Fellow of University Grants Commission. In fact, he did PhD, BTech from Osmania University. He was my alumni from Osmania. And he did MS and PhD from IIT Madras. So particularly Dr. Raghavan, he was also a distinguished fellow at many universities, Anna University, Indian Institute of Technology, Kharagpur, and member of Research Council, GAIL, IOC R&D, NCL Pune, RRL Bhubaneswar, CFTR Dhanbad, CPPRI, Shahanpur. He was successfully coordinated India's unique biotechnology incubation center at Genome Valley, Hyderabad. He was the president of Indian Institute of Chemical Engineers, AP Academy of Sciences, Vice President, Academy International Cooperation of Indian National Academy Engineering, one of the reputed professional chapter, Federation of Asian Biotechnology Association. Dr. Raghavan visited more than 25 countries. So maybe more than that, North and South America, Europe, Russia, Caribbean Islands, Africa, Middle East, Far East, Southeast Asia regions under bilateral and multilateral cooperation agreements, European Commission, Hungarian USSR Academy of Sciences, UNDP, UNIDO, Commonwealth Sciences Council, Japanese Institute of Chemical Technology, many more laurels he was to his credit. Dr. Raghavan was the recipient of Hindustan Lever Award of Most Outstanding Chemist of Engineer, NRDC Invention Award, Promotion of Biotechnology, Pilot Officer Dr. D.V. Rangareddy Gold Medal, J.N. Sinha Roy Memorial Award, Chemical Technology Foundation Award, Naidamma Gold Medal Award from AP Academy of Sciences, and also Institution of Engineering Award for Outstanding Scientist. In fact, he left to heaven on 12th of October 1947. It is befitting to organize the memorial lecture for his immense contribution. None other than my former colleague Suma Varughese. She is agreed to deliver the Raghavan memorial lecture. I think she also closely connected Raghavan. Maybe she was scientist at E and F level when Raghavan was there in DRDO. Mrs. Suma Varughese, she is presently Director General, Outstanding Scientist, and Director General, Microelectronic Devices and Computational Systems, DRDO Labs. And presently she did, in fact, she did post-graduation from Mysore University and also MSc Engineering from Indian Institute of Science, Bangalore. So Suma Varughese, particularly, she contributed 33 years to DRDO, and she joined almost Scientist B in almost 1988. Okay, so her area was the first indigenous planar near field measurements facility, Akash radar antenna, and also airborne maritime surveillance radar. So she joined after, I think, she was promoted during my period as chairman RAC. So congratulations to her. And Center for Airborne Systems, CAPS, she joined in 2004. Since then, very important project she was administering as the project director. Airborne Early Warning and Control Systems, one of the flagship program of DRDO. And later on, 2017, Indian Air Force absorbed this technology, one of the few countries possessing this technology. Airborne Early Warning Control Systems. And she is the recipient of various awards like NRDC National Award, J.C. Bose Memorial Award, IET, and also M.N. Shah Award of IETE. And she also received 3 awards from DRDO, Path-Breaking Research Outstanding Scientist, similarly Agni Award for Academic Excellence, similarly for Performance Excellence Award from DRDO, Minister of Defense. She consented to deliver Dr. K.V. Raghavan Memorial Lecture today, and she is speaking on NETRA, AEWC, Airborne Early Warning and Control Systems, a journey from concept to operationalization in DRDO. I think she will deliver about the lecture for about 30 minutes. Before requesting Suma Varughese, I request Mohan to say a few words.
I think we'll start your lecture. We'll start.
Good morning to all the eminent sitting here, and I thank National Academy of Sciences India, Hyderabad chapter, and Academy of Science and Technology in Communication for giving me an opportunity to share with you the journey what I have gone through for 15 years for realization of Airborne Early Warning and Control System called NETRA, from concept to operationalization of the system. Well, let me start the journey with, it was a cold day in February 2019. There was an unsung hero that emerged during this time. We have seen a lot of comments about how our Air Force managed to shoot down the F-17 aircraft during the Balakot strike. As rightly brought out by Professor Mohan here, I should say when it comes from the foreign press, it has a different impact to the Indian audience. And I should bring out here that it appears to be just how the aircraft was used during the shoot down in late February. According to the reports, the Bison was in air with Mirage 2000 and Su-30s, and maybe most important, the Embraer-based, 145-based DRDO Airborne Early Warning and Control System. The aircraft is not only able to get the God's eye of the battle space, including spotting low-flying bogies, detecting, geolocating the enemy's radar and communication emissions, but it can share what it sees via the data link or a voice direction with Indian fighters. So this was the system that was delivered, and the men behind this are the unsung heroes along with the system I should bring out. Well, in the history of military warfare, victory always depended upon the early warning that one side got for the deployment of the opponent parties. This started not today, way back in 2003 to 2002 BC, when one of the kite designer named Musi lifted the man on the kite to get the enemy's locations. Since then, there have been many innovations that has been brought about. We have seen the reconnaissance balloons that were used, deployed for coal barrages during the American Civil War from 1861 to 65, and tethered balloons that were used for reconnaissance during the World War II during 1939 to 45. Seeing the advantages, why there should be an AEW&C system or an AVAX system, came with birth of the AVAX system way back when US identified that low target detection capability is possible only with an AEW&C based system. As we see the gray portion of the graph, this is what the ground radar gives the coverage. But when you have a AEW&C system, it changes the total battlefield scenario for taking a better action. In fact, the development of AVAX in US started in 2000, it was against a war of 2006, which started in 1963, and we see that it had taken a long time for them to deploy in 1978 in the initial operation clearance phase of it. Subsequently, it was used in the Gulf War, and that is when the world woke up to the amazing technology that this can offer, where the system offered critical battle management for attack of enemy ground targets. It could handle the close air support coordinations, combat research and control was possible, and it could manage the airspace with all the aircraft flying around, and data link and communication for relay to the ground forces to carry out the operations. Seeing this, India decided way back in 1991 to start, though the preliminary studies had started almost in 87, 88, but a formal program was given to India where we started with Airborne Surveillance, Warning and Control System, then called the ASWAC program, where we tried to modify a Abro aircraft and mount on the top radar systems, data handling and display system, navigation systems and data communication systems, and the complete integration activities was happening, and we were in a very preliminary stages at that time, bringing the systems together. And the sad thing happened on 8th of January 1999 when we lost 4 of our own scientists, colleagues, during the phase of flight testing, along with 4 Air Force warriors who died during this crash. Any crash, it has a lot of implications whether India should continue with the program, not continue with the program. There were many challenges that was forced upon us, but however, we decided that we go with the next program. What I would like to bring here is, as we see in the previous slide, it was a dome which was mounted on the top of the aircraft. This was all mechanically moving radar so that it could see the 360 degrees of the battlefield area. So if we see the Boeing E-3 Sentry, which is a NATO AVAX today, Hawkeye, again with NATO, and also China too developed KJ-2000, which was a rotating radar for giving a 360 degree view. But with the advent of technology, what happened was Sweden developed a different kind of a radar where you didn't have to move the antennas to look at the area, but you can electronically scan the beam to the interest of where you want to see the item. And we have seen that there is few developments that has happened, and Boeing Wedgetail, which also, though it started in way back in 63, could launch their first AVAX system only in 2010, which they have given it to Royal Australian Air Force. So with this new technology, India decided, because both Hawkeye and E3 Sentry carried large rotating radomes housing mechanically steered antennas. This posed a great challenge when it is mounted on top of an aircraft, and the advent of electronically steered antennas gave an advantage over graceful degradation, better energy management, and inertia-less scan and performance enhancement. What I mean by that is, like you can throw, it is like an eye, how you can look where you want at whatever time you want. Though you are limited by, you can't see the back, but you are limited by that, but you can see and you can stare at an object which is of interest to you. You can spend more energy and time on the target that is of interest to you. These are the advantages that came up with the development of AESA based system. So, and also because there was no single point failure, and it gave an enhanced reliability to the radar systems that are developed. After the crash, when we were looking out on what kind of a system this whole AWNC has to be built, what kind of an aircraft we have to build, we went around looking at some of the aircrafts that were modified for this purpose, which are small in nature and we could be used. So if we look at it, we thought we will go ahead with what Brazil had then developed, where we have an radar system, an IFF system, an ESM and a CSM. I'll explain to you what each system does basically. Two types of data link and a voice data link, a self protection suite, and an operator to see what exactly is happening on the airspace scenario. But however, when the Indian system started emerging around this, the requirement grew beyond the size. And one of the challenges of having this great requirements is that swap is an important aspect on any of the airborne applications. Swap, I mean size, weight, and power. These are the critical parameters when we mount anything on. So as we keep increasing many things, there are other challenges that come into being, where it calls for structural reinforcement for radar installation, new kind of interior arrangement, electrical power enhancement, and also another thing, as you keep mounting the aircraft with more and more number of systems, the height it can achieve becomes a premium. And you know, it's a trade-off what we have to go ahead with. So the cruise altitude could not be reduced beyond 30,000 feet because we wanted to clear the Tibetan plateau. So these were some of the structural enhancements that had to be done to the aircraft, and also carry out an internal layout to handle all the electronics. When we say electronics, it should have an efficient layout for operation of the users. Weight and CG balance comes into picture when you are putting on top of the aircraft. The ergonomics of it, how you have to deal. So if we look at it, we started working around this kind of a thing. What I would like to bring out here is a system has to be thought as a system. It cannot be thought bottoms up, it has to be driven top down. And to have this approach, it takes a lot of effort that had to come in. So when we are planning to build a system of this nature, we also have to see what would be its use, so that it is built for the use of the operators and not as what designers conceive or perceive the system. So if we look from the overview of the system, we see that if an aircraft is flying around, it should be able to detect and track targets which are in airspace scenario. We should be able to identify what these targets are. We should be able to classify them, whether it is a friend, a foe. We should be able to say what kind of a target it is, whether it's a fighter or a helicopter or any other class of the aircraft. And to define the electronic order of the battle, we should be able to sense the signals in the air, both in communication band and in the electronic band, to say, yeah, these are the enemy radars, this is the conversation that is happening, all these things. And finally, to assess the threat against our own vulnerable areas and vulnerable points, and carry out interception of these targets in case it poses a threat against our own assets, and to handle the battle management, how the battle should be fought, along with guidance and recovery of our own assets. So if we look at it, it can also act as a network-centric warfare, which is the buzzword of today, where it becomes an element and it feeds to the commander's room what is happening on what is being seen on the aircraft. So this was the concept with which we started conceptualizing. The challenges are many, I should say. So with the airborne early warning and control system, the key functions as we defined: search, detect, track, carry out multi-sensor data fusion, identify and classify, guide and intercept, fighter allocation and intercept control, carry out the communications over line of sight via satellite link or on the voice or data link, and carry out the command and control functions to handle how the complete system control happens of all these systems. And we have sensor development that has to happen in tandem with what is happening, like the active array radar system, which was handled for the first time in the country, identification of friend of foe system, electronic countermeasure for sensing the radar signals, communication support measure for sensing the communication signals, and to some extent search and rescue operation. And since it's a very complex system, as we are seeing, it has to have an operator training station, a mission planning station, and a ground exploitation station. So when we look at the aircraft, today what you're seeing looks more like a porcupine because of lot of sensors that has been put onto the aircraft. What we see as black is the actual radar, actual antennas or projections that are available on the aircraft. But it added lot more, bringing down the performance of the aircraft in terms of its structural integrity, its aerodynamic properties. Everything had to be looked into. So if we see, we have struck out many of the antennas from all these systems, and also at the belly of the aircraft, many of the antennas have come. What does it make is basically simultaneous operations of all the systems and interferences. And what you can see, because it blocks the field of view for you when you are looking at the other sensors, and the body effects of the aircraft itself is a body. It starts radiating by itself because of the metallic structure, and how you can handle all these things. So this was one of the challenge. We see that a small mobile phone next to the radio, what kind of interference it generates. So to get a good signal, this was a major task that was envisaged and taken up. As I was bringing out, it's a complex system. We cannot do this individually as a single lab too. So the expertise that were available in the other DRDO labs were leveraged for this purpose. While the aircraft and the AWNC, the radar portion of it was handled at CAPS. The other sensors like communication and CSM, ESM, etc. were carried out by our sister labs to arrive at what should be the system performances of these aspects. Coming to the core technology, I should say that antenna itself, which is mounted on top of it, is almost around 10 meters by 1 meter and weighs around 1,600 kgs. So to handle this kind of, and we had never done this before, and we had to give a ballpark number beyond which we cannot exceed the aspects of it. So it called for a various technologies that we had to look into, because the first time in the country this was being attempted. One is basically from the aerodynamics point of view, the external flow, and the electronics. We decided to go for a air cooling system. So the internal flow for cooling of electronics also had to be decided based on this. The electronics and software in terms of radome, MIC and embedded technology, the mechanical aspects in terms of air loads, lightweight, shock and impact had to be considered. And since it is exposed on top of the aircraft, the other environmental factors like rain, lightning, erosion, electrostatic, temperature, icing, whatever is possible had to be considered when we were designing the system. Electrical and EM properties in terms of power supplies that has to power up this radar. Almost up to around 100 kilowatts of power had to be powered for the systems, and also from the point of material and manufacturing had to be carried out, along with other impacts like bird impact that can happen to the aircraft and can bring the aircraft down. So I should say the complete technology was first time, and it was new, and of components when we started developing this system. That posed a bigger challenge. So from the point of thermal management, when we were looking up for the air cooling system, we saw that once you have an inlet of air that has been taken for cooling of the electronics, the rainwater too entered into the system, and it can short the circuits. So how do we do it? Considering the maintainability of the systems were carried out, and for the first time we could see that, and sometimes when the air rushes, some of the components may get better cooled and the last component may be starving for air. So this was one of the critical design that was done during this period, though using the simple concept of your tandoori chicken roaster, I should say. So another major place where we got into the problem was on the building of the transmit-receive multi-module, which became a crucial point when we started building. This is the critical component of a ASA-based system, and this was indigenously designed from the available commercial power amplifiers that were easily available in the country, but the design was indigenized to see and indigenously made to see that we can use this, and today I should say DRDO has a patent on this technology. So if we look at it, there are more than around, I should say, 150 components that has to be put into a small area, keeping in mind the strength and the maintainability, which are kind of anti or oxymorons to each other, and we had to do it. And another innovation that happened was, if we see on the side of the screen, most of the imported systems have a radome. We can see a radome that protects the antenna for carrying out the operations, and whatever is the impact that happens first to the radome. And here we decided that antenna itself becomes a structural part. So that was another challenge where we went with a cladded radome concept, which was realized. I should say this, we worked along with ISRO to realize this concept, and we got other advantages like the loss factor, which is an important thing from the radar point of view, come down to a large extent. And there was speculations how it would work. It may tear off and have other implications. At that time we subjected the whole thing to lightning test, where we conducted the lightning test to say that it is safe for flying in air. So this just gives a glimpse of, there are around, I should say around 3 kilometers of cables inside this small place packed together, and we had to in detail work out how the assembly of the whole system has to happen to arrive at this system. The next studies what we had to carry out was ice, because we know that these aircraft will get deployed in Himalayan region, and one of the things is ice, and once there is an ice accreditation, there is a problem for flying of the aircraft itself, and it is quite detrimental. So we carried out the studies. This we did it along with the aircraft manufacturers, where we found out where the ice accreditation can happen and give a de-icing technique for removing the ice on the system. So the ice accreditation areas were discovered, and we carried out this test along with that. The next came the bird hit strike. What can happen to the bird? And we see here the first slide where it has broken up totally. So we worked out again, and we found that the bird hit test went through with the design. Why do we do all these things? Sometimes when we look at it, Unlike the military certification that most of the aircraft had, because we were working with Embraer, which was a transport class of aircraft, the civilian requirements came into being. So in military, some things can go wrong, it's still acceptable. But in a civilian domain, nothing is acceptable. So when we started working with them, there is a federal aviation body that comes and certifies that it is capable of taking this kind of loads. So there was a lot of lessons that we learned, and I should say this program has opened our eyes to how the transport industry outworks on some of the minute aspect what they take care. Just to name one, we were assembling the parts together, and the contract was such that we were supposed to give this as a customer to them, and they were supposed to give the aircraft to us back. So there was an issue about, if you don't give it on time, what would be the penalty on you? That was the whole issue. And we accepted to go with a liquidity damage on us. And when the inspectors came, every part got rejected. Every part got rejected. So we were wondering what it is. We took experts from HAL, everybody. They said your part is perfect. So we were thinking they are playing some game because there's a delay on the aircraft side. And I should say, very nice people. They came, and when I said why this part is getting rejected, they sat with each part and explained. And it was as simple as a pencil mark on the system where they said in the long run it leads to erosion because of the carbon and the aluminum what you have. So we don't accept this part. So that is how we refined our system. And I should say, when by the end of 6 systems what we developed, he said it's as good as Taj Mahal. So while structurally we were handling on the other aspects, we had to handle from electronically different aspects. And since this was the first time in the country, we had many challenges of how to test this system itself. What is the parameters for testing this system? So with various literature that were available to us, we carried out the first testing of this system. And we see that when the system starts, it is all disturbed area. Slowly we build it up to see that you get a homogeneous system, so that you can coplanar waves can be generated using this, so we can go for a better electronic scanning of the system. Meanwhile, the mission communication system was developed, where an additional feature we started providing was to have a radio relay kind of operation that was provided, wherein a fighter who wants to talk to the other fighter could use us as a relay station and talk, so that his range enhances. So these were some of the things we started doing on the go. And of course we have both the satellite communication and the line of sight communication that was developed with DEAL. We have communication support measures developed along with DLRL, and chaff and flare dispensing system was also brought out, so that when there is a missile is approaching, we are able to detect the missile and put out the chaff to decoy, as a decoy for missile approach warning systems. When we have 9 or 10 systems, there is an orchestrator that is required. And the orchestrator here is the mission computer system. Basically, the functions here are, we have to monitor the health of all these systems together, carry out the mission data that is get pumped into the system to the mission controller from all the various sensors what we see. And these sensors has to be time synchronized to say that yes, this happened at this moment, and I saw it at this moment, so somebody sees it at some other moment. But how do we fuse this data together? And tactical functions had to be carried out along with the users. I should say we as scientists think differently, but operators think differently. And there was a lot of gap that came into picture, and we had Indian Air Force sitting with us when we started developing these systems. And we decided to go for COTS-based hardware because it is easily upgradable in case of an obsolescence management. So one of the things of many systems here is, like, we see Earth or an environment, we see that there is energy. The energy impinges on our sensor, which looks at it as signal. The signals has to be deciphered as data. Data as state vectors, and we have to name it and then turn it into knowledge. This journey had been done using the multi-sensor data fusion concept because this became an ideal candidate for multi-sensor data fusion, because all the sensing that these things are bringing out could be integrated. And when we are presenting to the user, I'll just go to the next screen. User, we cannot have his screen cluttered with many information coming. So an entity in the space has to be identified, classified, and given as a single input to the user. And a great deal of software had to be developed for this purpose. And this is one of the screenshot view of what you see. Typically, this is in the sea region where we are able to pick up the ships and some of the aircrafts that were flying around. So whenever an operator goes for a mission, we need to plan what the mission should be, how the mission has to be done. And after coming down, we have to see how the data is handled and what kind of a data is handled. So we have developed a huge mission planning station for them, where simultaneous planning by multiple operators is possible, and also provided them with a training station where they can train their operators on the existing data, where we can plow back the data that has been brought out from the missions, and also helps us in improving their tactics down the line. So both this has been done. And the ground support station that supports to the integrated command and control center of Indian Air Force, where when the Balakot strike happened, the chief was able to see what was happening on the top. So to that extent, it has been carried out. So this is one of the first sortie what we had in 2013, with followed by, apart from these campaigns, from the other campaigns like, the icing campaigns that was carried out for ICE accreditation and getting an icing certification. We had to prove the system at high altitudes, like operations, whether it is possible from Leh and Ladakh region, basically because of the rarity of air there, whether the aircraft can take off from that heights. We had to do the safe separation checks that had to be done. And for the first time, I should say, a transport class of aircraft has gone for a refueling operations, where we could refuel the aircraft within 9 minutes, holding in the air, and extend the operations by another 3 to 4 hours. This was made possible. And as brought out, our country is so wide, vast, with its own landscapes. So we have carried out various campaigns at almost different parts of the country to prove that, whether you fly in the deserts of Rajasthan or in the green vegetation of Chabua, you can still have the same performance of the system. This was carried out as part of it. I should say with that, with almost 20 years, we came out like Phoenix. We have deployed our system within, say, 15 years, and it has been operationalized. I grew up with the system, learned a lot of lessons, right from a system engineer to the project director, then on becoming to program director. It was a great journey, and the journey was that I could see from what we conceived as a small thing becoming a huge operational asset for Indian Air Force. And I thank here all of you for giving me an opportunity to share this journey. Thank you.
Any one or two clarifications or questions? Normally memorial lecture, no questions are asked, but we can permit one or two. Maybe most of you are scientists, not in engineers, so yeah, you want my...
How do you benchmark our systems against our competitors, and how do you extend its performance and efficiency, ma'am, actually?
One thing I should say is benchmarking basically comes from the PSQRs what has been given. And our systems are generally looking different. I mean, we don't have much exposures to the foreign systems, especially in this areas, because we are already denied even the smallest component for realization of this. But as I say, the proof of the pudding is in eating. So once we say that, you know, we have met your QRs, what is given by Indian Air Force, that is one way of looking at it. And also, I got an opportunity to visit the NATO AWACS at some point of time during the program, where the sideline talks gave me some inputs into what was happening. And that is when, you know, it gave us confidence, yes, we are on the right track and we know how to do it. Thank you.
Thank you, ma'am.
Dr. Suma, your talk was excellent. Integration of various systems, computation, aeronautics, electronics, sensors, you brought the whole thing into very simple understanding for all of us. One more just point I want to make of the integration of different areas is that in this entire area, biology is out of situation, but biology made a contribution here. When you say bird hitting is a major event. Many aircrafts suffer from that. So CCMB Lakhons has investigated the entire aircraft area, airport areas, to identify what are the trees present, what are the birds which live there. So there's a barcoding done correlating the tree plantation versus this thing, identified eco-engineering with which the bird hits have dropped completely. Okay, so something any corner can contribute. Today's technology and science is that anybody can contribute. Yeah, we are very happy to see that. And as you are asking about the performance parameters, how do we compare? Yes, comparing is difficult, but the proof of pudding is in eating. As she mentioned, Balakot is a proof. Balakot is a proof that we work. Yeah, right. Thank you.
I think Suma Varughese has done a wonderful job right from concept to operation. She has, in fact, she had wide experience in radar antenna in LRD, Bangalore. I think those who are not familiar, DRDO, I think there are about 48 laboratories are there in the country, about 8,000 scientists. Generally, whatever the technology developed by DRDO, the services you have to convince them. So CSR scientist needs a patent, transform into industry for productionization. But services acceptance is very difficult in our country, because the Indian Air Force and Army or Navy, they have a stringent, normally their tendency is to go import the system from abroad. So long journey of DRDO, particularly Bangalore DRDO labs contributed for this important system of airborne early warning system, which is accepted by Indian Air Force. I think almost 2 years back, 2017, still operational going on. And other one is the Tejas aircraft. Tejas indigenous aircraft, so in fact conceived by Bangalore lab. AD is there, Aeronautical Development Agency, ADA is called ADA. These are Tejas aircraft and airborne warning system. And Hyderabad labs contributed for missile, Prithvi missile, Akash missile. So strategic and tactical missile systems are contributed by particular DRDO Hyderabad labs. Like that, now acceptance level by service is 40%. Earlier, almost 10 years back, only 1%, 2%. Now the acceptance from DRDO is almost 40%. I think we have a long way to go. The technology is changing, because basic basically, earlier we had a lot of, we used to get any components from abroad. So we used to mostly depend on Israel. So technology, Israel is the one dependable country where we get technology. So they think this particular airborne early warning system, basically it's putting a radar into the higher altitude, 30,000 feet. Because the hilly regions, enemy aircraft coming in, we should be able to sense maybe 100 kilometers, even 400 kilometers away. Then only you can able to give the command control system data. So a lot of technology goes into this system, particularly sensors are there, the lightning systems is there, ice formation is there, bird hit is there. So much science it goes into these technologies, not engineering and technology alone, but entire science spectrum is required for these kind of systems to develop in the country. Fortunately, we have almost 42 scientific laboratories are there, CSR, and about 48 DRDO labs, and each one now the dependent. Earlier used to be feel ego, everybody lab think they are contributing. Now I think mindset is changing, they are coming closer. I think material science also very important. She was telling that lightning, the aircraft may break into pieces because of lightning. So several technologies goes into that. I think her boss, Mr. Christopher, I think Suma Varughese, they worked almost 2007. In fact, Indian Air Force has agreed the proof of concept. Then after that, now it's 15 years. I think the systems are up to Indian Air Force. I think a lot of journey by CAPS Bangalore, Center for Airborne Systems Bangalore lab. I think I would compliment Suma Varughese for particularly presenting such that simple way, so that everybody, non-engineer or scientist, somebody could able to understand what is the concept, what is the operation, what are the problems uncovered. I think she did a good job, particularly presenting, befitting to the Dr. K.V. Raghavan memorial lecture. Dr. K.V. Raghavan contributed immensely for particularly scientific community. I think we remembered him on this day. But in fact, he born in October, also died in October, coincidence. So it's befitting. On behalf of the organizers, I would like to thank Suma Varughese for excellent job she presented. And in fact, I would like to personally thank Dr. Mohan Raghavan, good friend of mine. So, and also Narasimha Rao, particularly the organizing this important women scientist conclave. So I request Dr. Mohan Raghavan to add some few points.
May I now request Dr. A.V. Ramarao Garu to please come on the dais to present a memento to the speaker. And if Mrs. Raghavan also can join us, it will be nice.
All the awards I got for my science. Only later they started requiring. It took a long time.
Thank you, sir. Thank you. Thank you, Professor Reddy, and thank you, Dr. Ramarao.